recording, setting up here. So, yeah, this is going to be a continuation of last week. Last week we're talking about chapter 6, and I didn't get that far, so I wanted to do a few more problems out of chapter 6. Let's see, chapter 6 continue. Right. Yeah, so let's dive right in. So I last ended talking about method of sections. So I wanted to go back into the book and do a few more problems using the method of sections. Method of sections. All right, I'm gonna go ahead and do 635. 635. So basically, it says determine the force of members EFC, FBC, and state if the members are in tension or compression, right? Kind of expected something like that. This is our structure. Alright, let's get this down. Call this one A, B, C, D, F. Got a force this way, up to 8. Got another force this way, 4 kilonewton. Okay. And we know the distance from here to here is 2, here to here, and from here to here is 2 and 2. And distance from here to here is 1.5 meters. Okay, so let's see, we got it down. And details here, there's a ball. There's a ball down here. The structure is basically on that. So we know that means it's just going to be a normal force. So let's go ahead and start there. Well, actually, no. What was the question again? The question was determine the force in the members. I guess I'll label those members. And EF, so EF in this member. CF is this member. And BC, which was BC. BC, okay. So right, and we're going to use method of sections. Okay, so let's go ahead and see how are we gonna cut this up. I think we should cut it like this. This one, let's cut this one forward. It's like this. So we cut it. But I think that cut gets each one of them in there, right? Yeah. So I'm gonna cut it like that so I can see this force, I can see this force, and I can see this force inside of those. Interesting. I didn't bring my notes with me today, so I just wrote down the ones I was gonna do. Yeah, so we're gonna cut it down by this section. So all we have is this top structure here, and that top structure looks something like this. cut right there. Let's cut right there. This is let's see. Okay, so now we know there's some, well, there's a force this way. All right, that's the force, the 4. And then there's a downwards force from, well, I'm assuming it's downward, but we'll find out if it is or not. Call this downwards force. Let's call it EF basically, right? Goes from E to F. Okay. So that's our free body diagram for that guy. There's another force offset. Actually, there's one here and here from this guy. I guess I'll say this is one, this one. So force, let's say that's CB. Because it's coming from BC, that one, and then this one is force FC. Okay. So we cut it like that. We cut out this force, so we don't even have to see that. So we just have these forces here, and then this guy. Well, yeah, because we're not doing the internal forces. We're just doing the external ones. So yeah, okay. So let's do our sum of the forces, and we'll do sum of the forces, all right, and we'll do sum of the moments. So I like to start with the moments first. I mean, this time I start with the sum of the forces in the x. So sum of the forces in the x, and I think the moments would be actually a bit bigger. All right, all out here. So sum of the forces in the x direction is equal to 0, right? That's equal to 4. Got 4 to the right minus okay, so boom, that gives us 1. Let's do sum of the forces in the y, but I don't think that would give us anything. It just gives us a relation. Minus the, right? It's just telling us that. Let's do the moments now. And let's do the moments about C. This would be about C. And I'm calling this way positive, set that equal to 0. Okay, so we've got a point C there. There's basically 2 forces that are going to be causing a moment, the 4 and the F, E, F. Yeah. So let's see, F, E, F looks like it's going to be positive, and it's over there 1.5. So 1.5. And let's see, F, E, F, the 1.5 came from here, right? And what else? What else? Oh yeah, the other one. So minus. So if you go up, that's 2. It's gonna be 2, 4. Okay, so that tells us something. It tells us that F, E, F is gonna be in. Yeah, for here we solve for F, C, F. That's gonna be equal to 4 kilonewtons. Here we get, let's see, that's 8. Add that over. 5. So that 8 over. That's that's 5. 3. Okay, kilonewtons. And what else? What else? So now we've found that, well, this tells us that BC should be the same thing. So, all right, once we solve for this, that tells us FEF and FBC are the same. So this is also equal to F is also equal to FBC. Okay, and it looks like I got all positive values, so that means if you look at this one, this FEF, this is going to be a tension. So FEF was a tension. And FB, so I guess they're both tension then. FBC and FEF, so both of these tension, tension, FBC is also, well, no, BC is going upwards. Let's see what BC over here. Yeah. Okay, so that wasn't bad. That was 635. Let's do another one. So next, let's do let's do 641. And I'll just draw it out first. So we got this bridge looking. Uh, that's not right. Okay. And we got these points that we're gonna call again. Start down being A, B, C. Yeah. We got these two forces here. That's 11 minus 22. And we know these lengths, of course, from here to here is 2. Is 2. Here. It's 1.5. From here to here is supposed to be 2. Okay. So basically, the question is for this one, determine the force of members. See? Okay, so let's label those on our picture here. FE, so this one right here. EB, this one over here. BC, that's this one right here. Yep. And Yeah, this is just those three. MBC. Yeah. Okay. So, and of course, determine if it's in uh, stress or tension. Okay, so let's cut it this way using method of sections. I guess the only one I see is right here. Slice like that. Yeah. So now we have our structure looking like this. This one point right here. Oh, let's cut over there. Go all the way down. Yeah. It's right here. All right, now let's draw the external forces on that guy. Of course, there's this 22 down right here. There's going to be some forces on these. Then over here is actually just the normal force. Well, because of the structure, these are just balls. It's just a normal force upwards here. Let's put that in. Like that. A normal force. 40. Okay. And of course, from the structure here, it's going to be on this way. As opposed to this way. And that's going to be force B, EB. From EB. That's going to be force F. Okay. And let's say this one's going this way. Let's call that F. What point was that again? C. CB. Okay, so those are external forces there. Got these. And now let's we can do a support reaction for point A, I guess over here. Well, no, let's just do some of the moments about C and D. Actually, this only has, because when I know what that is, when I find it there, don't know. I don't know. Let's start with, just pick one. Let's start and see what it does for us. Let's do about E at the top, since we're right there. Some of the moments about E at the top. So about this point. Yeah, that way I can ignore those two forces. Okay, so moment about C here. Look, this is gonna cause a moment. This one right here, I'm gonna ignore these two. This FBC, which is down here, FBC is gonna cause a torque. No, this downward force is not. Okay, I see what that does. It's gonna be the same thing. So that's so starting with the normal force, that's 2. It's the right over there times ND. And what's that minus? Yeah, minus. It goes down to FC. Okay. Yeah, it's close, but can't solve for anything with that. All right, well, let's do the moments about. I guess we can really do the moment about any point on this thing. Which one would be the best? Actually, let's do some of the moments about A. Because if you look at the overall structure, if you do some of the moments about A, of course we have these two. It would give us the normal force. And there's actually two supports here too. So there's actually a force like right here and here, right? From that guy's surface. And of course it's a normal force over here. Yeah, so what if we do the sum of the moments about A? That would actually give us this normal force. Ooh, okay. Let's do moments about A. 0 equals, all right, I'm calling this way positive, so looks like that's going to be in a negative direction. Times 11, going that force of 11 is 2, 2 times 2, and minus, so it's not 2, 3.5 times 22. And that last one, the normal force is going to be positive. Okay, so plus 2. Let's see how far is that? 2, 2, 4, 5, 5. Boom. Okay. Let's solve the normal force now. Force at B. 18 kilonewtons. Okay, so we have the normal force now. So now let's take that normal force, see if we can plug it into this equation actually, the moment about E, and we can solve for FBC. So I'm going to take this 18, plug it in up there, and FBC. Wait a minute, interesting. If you look at that, it just says it's equals, right? This right here just says the normal force is equal to FBC. These two just cancel out. Yeah, okay, so FBC actually equals, and they're both lazy. Okay, nice. Okay, so now let's do another. I could do the sum of the forces in the X direction. I guess we got this weird one that's at an angle here. This one, this FEB. Something like that. But let's keep doing some more moments because I think those help. So let's do now the moment about. What if I do? Yes, let's do this. Let's do the moment about B. Because I did A, let's do B next, which is this way. 0. Okay, it's a moment about B. Hmm. Oh, wait. There's a force up there. Well, there's some force in the X direction too. That is definitely stuck in force. So, real quick, some forces in the X direction. Let's just F, F, minus C. Yeah, that's not going to do anything for us. It's, it's going to be the X component. Uh, the X component. So I guess we could find that because we know what kind of triangle it is. Is it 3, 4, 5? It's like a 3, 4, 5. Yes, 3, 4, 5 triangle. Okay. Um, force BC and force. So this would be 18 and 2.5. What's that? Minus 1.5. 11. 22. I mean. Yeah, okay. And what else? Oh, then we can ignore force EB because it's parallel. What's along the line of action number? Okay. So then we also need that force. Yeah, so plus. No, it's actually minus plus. That one's minus. Okay, we can actually solve for that. Interesting. So force E divided E. It's supposed to be FE. What's F? Calculator. Okay, so we've got. I think that's the last one. No, it's not. That's not. I did. I did. Okay, so we got this force now. So we got that one. Uh, this one. Just this middle one. Middle one is this one here that's at this angle. This one here. And so yeah, I guess we can actually solve for here. If you look at this, some of the forces in the x direction. I know F E. I know F E. F E. I know F B C. I know F B C. Could plug both of those in and just solve that x component there. But let me also do some of the forces in the y. Some of the forces in the y is going to got that number force over there. That's 18. So that's what minus 22 force again. Plus the y component is right here. Finally, FEB. Okay, so method of sections. That was a tricky one. That went into the angle. Okay. So hopefully now, before we were going method of joints. So today I just want to do a few more problems with using method of sections. I'm going to do two now. Let's pick one more to wrap it up. I should do one in 3D. That's fine. Let's do a pulling. 64 is a pulling. It looks like this. So this is a pulley. Looks like this. Connect it down there. Okay, looks something like that. Not really pulling and then pulling this way. So the force required to pull, required to hold this 150 kilogram crate right here. Okay, so with this pulling, how much power or force do we need? Excuse me, how much force do we need to hold up this box here? Okay, no. It's not happening. Okay, okay, the idea. All right. Uh, okay. Sheesh, that's off the draw, right? So basically what we're going to do here, we're just going to apply basically our equations of equilibrium along these pulleys here. Along these. So, and here's our box here. All right, so this is weight that's coming downwards, mg. And the pulls. So if we just look at this first pulley, I call it pulley A right here. Let's analyze this pulley first. All right, it just looks like this. So let's call that tension A. All right, so it's going to be a TA here. And the one thing about pulleys is tension is the same on either side. And we got the weight right here. Okay. And now let's also analyze the other side of the pulley that's over here. Here, right? Basically looks something like this. Right over here is that force, that pull. Okay, so there's going to be a tension here. So on this side, it's going to be the same pull, basically. So P, P. Okay. So if you look at the pulling, I guess the key here is to notice that this part of the pulley here and this part here, if you look at it, it's basically connected to here, tension A, right? Just wraps right around there. Okay, so we can actually call this tension TA as well. Okay. So now we can do some of the forces in along the direction. So like for this one, it's going to be along the Y, and for this one, it's going to be basically along this direction here. So they kind of work out to be pretty easy. So for this one, some of the forces in the Y, 0 equals 2TA minus W. And for this other one, I guess I'll call it Y prime. Y prime along there, right? This Y prime equals 0 equals TA minus 2P. Okay, cool. So we can solve for P then. So P right here is going to be equal to TA divided by 2. And we know TA is equal to the weight divided by 2. Okay. Let's plug that in. That equals 1 over 2. Weight over 2. Okay. Weight over 4. P equals whatever the weight is divided by 4. Interesting. Huh. Very interesting. So you only have to hold it there with a fourth of whatever the weight is here. So that was a cool problem. That was fun. So I'm into with that. Yeah, I'm into with that.